All right, welcome back, folks. And today we're continuing the lecture that we started last time. Maybe I'll just flash up the title slide again for the recording. This is lecture 15 and 16, so today's 16, cameras and lenses. And we went through last time a bunch of things that were based on primarily, a lot of it actually was based on pretty a very simple geometric construct around the field of view, the angular field of view that's created by a specific sensor size and a lens that has a particular focal length, right? And I tried to work through a lot of the and show you the ways that plays through into the compositional elements in the kinds of pictures that we make. And those very simple relationships actually capture a lot of the relative geometric size of objects that we see in the photos that we get and how that affects the thinking of photographers. Today, I want to get into the nitty-gritty details about lenses in particular, the more technical elements of lenses, and how they create effects of focus and depth of field and how to calculate these things. And so this is a little bit like an optics 101 here, okay? But a little bit from a graphics perspective. And in particular, I'm going to tie it through to how once we understand how lenses form focus and depth of field effects, we can simulate those in the ray tracers that you're working on currently. So for assignment 3.2, one of the options, you'll have a few choices of parts that you can choose to do there. One of them will be on simulating camera effects and depth of field. I showed a couple of these slides at the end of last lecture. So a couple of key points. Real lens designs are highly complex. Okay, there's even smartphones have 5, 6, 7 pieces of glass inside them very typically these days in order to correct aberrations, as I'll talk more about at the end of today. What's an aberration? An aberration is an undesired non-convergence of rays. One of the most classical one really is spherical aberration. So you can see here a schematic or a cartoon of a curved surface here. This is called a plano convex lens. And rays of light drawn in blue coming from the left-hand side parallel and then refracting through this lens just due to Snell's law. And they don't converge to a point anywhere inside the lens. Okay, so there's nowhere you could put a sensor and get a perfectly sharp picture is the point. And this is just a natural geometric phenomenon of having a curved surface there. We'll talk about the ways that real lenses try to circumvent that problem by using multiple pieces of glass of different index of refraction and different dispersion characteristics towards the end of this lecture, just touch on that very large optical engineering topic. But what I want to concentrate most on today is actually building most of our intuition about focus, depth of field, and the appearance of those things from the thin lens approximation, from a thin lens model. Okay, so what is the thin lens model? It assumes an idealized version of a lens that didn't have those aberration problems that I showed you 2 slides ago. It assumes that all the parallel rays of light that come to some lens are going to refract perfectly to come through its focal point. Okay, geometrically perfect. And in this situation, that point where they all go through, at least the parallel horizontal rays as shown here, that's the focal point of this lens. And the distance of that point to the plane is the focal length that I was referring to last time. So the way to think about a lot of what we did last lecture was an ideal thin lens model, except that instead of a thin lens that has a finite height there, we assumed a pinhole, right? So one that had just a tiny opening centered on the optical axis right here. And it was a pinhole camera instead of a lensing camera. With this thin lens approximation, it turns out that we'll get a ton of leverage, both analytically, geometrically, and algebraically, as I want to show you, for deriving some of the key equations that you very well may have come across before in a physics class or an intro optics class, like the thin lens equation or the depth of field equations. The depth of field equations are a little bit more involved. But we can derive all of them actually geometrically from this Gauss ray diagram in a really, I think, very easy to understand and easy to remember way. So I want to show you that. And it gives us a huge amount of predictive power about how to interpret what kind of focus and depth of field or blur effects we're going to see in our photographs or our graphic simulations of photographs. Okay, so Gauss ray diagrams. What's a Gauss ray diagram? I'm going to show you here. It's a way of constructing the key drawing the key rays from an object in the world through a thin lens in order to figure out where the image of that object is going to appear, inside the camera, and how big that object's going to appear. Okay, and in fact, everything that you need to know in order to draw this diagram in terms of assumptions geometrically, I already showed you in the thin lens equation. All you need to know are that parallel rays of light that arrive at this camera parallel to the optical axis being, this line here, right? So all the rays that arrive parallel to the lens are going to get bent so that they pass through the focal point. It turns out that's symmetric. Whether you come from the left or the right, the lens is going to act symmetrically in that way. So I've drawn the focal point on the left and the right of the lens here. Okay, so let's start. The first lens we want to draw is, we can call it the parallel ray. It's the object I'll use in this cartoon is a little arrow that points up, okay? So we're trying to say, let's say we pointed our camera or our lens at this object here. What's it gonna appear? Where is it gonna appear inside the camera and be focused? Okay, so you draw a parallel ray, and we know from the ideal thin lens assumption, it's gonna bend and go exactly through the focal point. The second one is that we can draw a ray from that same point. We'll ask where that point on the object appears inside the camera. We'll just draw another ray that goes at a different angle, the angle that goes exactly through the focal point on this side of the lens. We'll call this the focal ray, okay, just to give it a name. We know that that one's going to get bent to a parallel line as well to the optical axis. Okay, so we got it here. And in fact, just these two lines are going to show us that the image of this arrow over here is going to appear on this side of the lens over here. Notice that this image of the arrow is a little bit further than the focal point. Okay, so that's going to be true for every real image that's formed for something in the world of any object. It's going to appear at a distance that's at the focal point or further away from the lens. And there's one more ray that we can draw called the chief ray that goes from any point on the object. It will go through the dead center. You could think of it as the pinhole point, all right, if it was a pinhole camera, through the dead center of the lens and traverse straight through. So that's going to converge as well geometrically over here, as you can see. Now, in addition, we know that since this ideal thin lens is going to take all rays of light from one side that come from a point and converge them geometrically perfectly on a point on the other side, all of the rays that you can draw that come from the tip of this arrow, anywhere, any ray that comes to the lens is then going to refract through as well and go through the same point on the other side. Those are harder to reason about, right? You can't reason about exactly what that refraction angle is going to be. But once you construct this diagram, as I've shown you here, to deduce where this image point at the tip of the arrow is going to be, you can draw all of the other rays if you want. Any ray that passes through here will just bend exactly to go through there. Okay. All right. So that's the Gauss ray tracing construction. And if you use this ray tracing construction, you can find out where any point on the left-hand side is going to, any point on the left side emanating rays is going to reconverge on the right-hand side. Once we've got this, we can derive one of the most important and famous results in for lenses, right? Which is called the thin lens equation. The thin lens equation relates to really important quantities that we very often want to know, which is that, okay, if I have an object that's at a certain distance from the lens, so let's say that this arrow here is at a distance z sub o for object, okay, in the world, I want to know what the distance is z sub I that the sharp image of that object is going to appear inside the camera. So I want a relationship between z sub o and z sub I. And it turns out that it's going to depend, as you might guess, on the focal length f here, okay? All right, so you might recall what the thin lens equation is. It's a pretty simple form. It's put into a memorable form so that people can learn it in an optics class, but it's not that common. The first couple of times I learned it, I definitely could not have derived it for you. I want to show you how to derive it here because it comes from this very simple ray construction. And the only other thing that you need is similar triangles analysis and a tiny bit of algebra. Okay, so we're going to go through it. So we're going to look at two similar triangles here. The first is shown here in blue. I got a question here. If z sub I is not the place for the sensor, then we will have a blurry image like the background. Yes, you're exactly right. There's a question that, if Here, if this is where the image of this arrow appears, if we didn't put the sensor there, we wouldn't get a sharp picture of that arrow. That's exactly right. We're going to do the analysis on exactly how blurry such a misplaced sensor would be, and that's going to be key to analyzing depth of field and circle of confusion. That's coming up a little bit later in this lecture. Okay, the first similar triangle is this one here. I'm going to give a name to the height of this object, okay, h sub o. It turns out that this is going to fall out when we do the algebraic analysis on the next slide. But for now, it's helpful to have this temporary variable. So I'll call this h sub o. And this distance here, right, is just z sub o minus f, because this is f over here, the focal length, and z sub o is the total distance from the lens to that object. The second similar triangle that we'll want here is f here, this length here, versus, I'll give this a name, h sub I. H sub I is just going to be the height of the image of this object inside the camera. Okay, so h sub I here is really just the height of this thing here. Okay, so by similar triangles, we can write down this really simple relationship, right? H sub o divided by z sub o minus f here is the same as h sub I divided by f. Okay. The next thing is there's another pair of similar triangles inside the camera. So let's do those. Okay, the same variable here, h sub o. In this case, this is f over here. And then we have this distance here, which is z sub I minus f. Because again, z sub I is just the distance from the lens to the image, I for image. So z sub I minus that focal length f here, this distance here versus h sub I. And we can write down another set of equations here representing that similar triangles relationship. H sub O over F equals H sub I over Z sub I minus F. Okay. All right. That's it for the geometry flowing from this Gauss ray, ray diagram. The next thing is we just want to simplify these diagrams to find the relationship again that we're seeking between Z sub O and Z sub I as a function of F. So what is that? Okay, so first of all, look at these equations. We can just simplify them all by moving some terms around to make H sub O over H sub I, right? We can just rearrange terms like this. H sub O over H sub I is going to be equal to Z sub O minus F over F. And similarly on this side, we get H sub O over H sub I equals F over Z minus F. So of course, we can relate the right-hand sides of these two equations here, and we get this equation. Okay, we're almost done. So now it's just really kind of what form do you want to simplify this equation to? I'm going to go through the next steps kind of quickly algebraically because they're all kind of trivial algebra, and it just depends on what form you want to put it in. So I'm going to move it into the form that is the classical form for the most famous form and typical form these days. And so, okay, one thing that I'll just note first here is that I told you this H sub O and this H sub I is going to disappear. Okay, they're gone now. You'll notice in this simplification here. So those are just helper variables, and they're not crucial variables in this relationship between Z sub O and Z sub I. Okay, so here's one equation. We can cross multiply here to get a form that looks like this. Z sub O minus F times Z sub I minus F equals F squared, which is kind of a nice symmetric form. Actually, if you prefer remembering this, feel free. It actually has a name. I'll tell you about that in a second. You can collect more terms, multiply out these two terms here, and then collect some terms, which ends up with an equation that looks like this. And then finally, you can recognize this form. If you divide through both sides by Z sub O times Z sub I times F, you end up with this thing over here. Okay, I also swapped the two sides of the equation. What you get is 1 over F equals 1 over Z sub I plus 1 over Z sub O. Okay, and this is the famous Gaussian thin lens equation. This thing over here, by the way, has a name to this form, which is kind of pretty as well. Maybe easy to remember. This is called the Newtonian version of the thin lens equation. All right, but this is, I think, by far the most common form, the Gaussian thin lens equation, and you'll see it in almost any optics 101 kind of course. You very well may have come across it before. Perhaps you haven't come across the derivation though. All it requires is the Gaussian ray diagram, assuming the thin lens assumption that all parallel rays will go through the focal point. Then you just apply, again, similar triangles and the algebra that's shown on this page. Okay, all right. So here you go, the thin lens equation. 1 over F equals 1 over Z sub I plus 1 over Z sub O. Maybe with a derivation that you may or may not have seen before. Okay, let's take a look at some of the properties of this because this equation is very simple algebraically. It captures, remarkably well the most important focusing effects of a real lens. and explains a lot about the properties of lenses that are nonlinear. Okay, focusing, the depth of focus and the depth at which you need to focus a camera turned out to be nonlinear. And that's captured by this relationship over here. And it's one of the most characteristic and unusual and characteristic elements of real lenses, real cameras, and real photography. Let's take a look at some of those characteristics, okay? Now here, this diagram, I'm gonna go just walk through different versions basically of Z sub O and Z sub I that match through this equation. And we're gonna consider in this case, actual focusing. Okay, so now imagine that we have a sensor I've shown as a blue line here. That blue line is going to be placed at a position so that it is capturing the rays that have converged from a particular depth in the world. If you think about it for a second, that means that sensor is going to give us a photograph that is focused on the depth Z sub O in the world that matches the Z sub I of that sensor here. Okay, I'm going to show you a few different Z sub I's and see what depth Z sub O's they focus on in the world. Question I got here, do we assume the lens is concave or do we assume it has no curve? Oh yeah, great question. So in this case, we do assume that it's a convex lens. Okay, so a convex means that it's bowed out in this case. Since it's a thin lens equation, it's called a thin lens equation because we assume actually that all the action takes place at that one plane in the middle. So it's in sort of in this model, which is idealistic physics model or optics model. It's a sort of infinitely thin lens, but its action is similar to a lens that has a convexity to it, okay, on both sides. It turns out there's variations of this equation that are simply generalized to include like, concave lenses and all other sorts of things as well. But those aren't going to be as necessary or important for us today, so I'm going to omit those. Okay. All right. Let's take a look at some of these pairs of things. One other thing I want to introduce you to is just some terminology. Terminology can be good or bad. Usually I try to avoid it if it's not necessary, but it's a very common term to call the Z sub I, the position inside the camera, versus the Z sub O, the object distance in the world, to be called conjugate distances, okay? This is not like conjugate gradients or the stuff. They're just conjugate in the sense that it's meant in the sense that they are related, okay? Conjugate, just think of it as related. And how are they related? Related through the thin lens equation, okay? So if we put Z sub I equal to F, that is the sensor is at the focal point, you can sort of see that, right? It's directly over this dot here. The sensor at that, you can see that the rays of light obviously converge, are arriving from parallel rays. If you reason about that geometrically for a second, you can convince yourself that what that means is that those rays are coming from arbitrarily far away. They're coming from a point that is infinitely far away. And different points actually on this sensor will take parallel rays at different angles, okay, that go out into the world. So this is actually taking a picture of things that are very, very far away. If we move the lens just a little bit further in this cartoon, okay, just this, what seems like a small distance here, then you can see that the focus is actually changed to this position over here. Now, one comment that I would make is that actually a huge amount of activity in terms of photography and camera engineering is happening between these two blue dots, these two blue planes here. Okay, a tiny change in the distance in the sensor here actually ends up changing the focus depth in the world a huge amount. And there's many, many planes of focus in the world between this one here and out to the world. How can you know that? Well, just reason about it in terms of the size of this lens. The size of the lens on your smartphone is only a few millimeters diameter. Even on the largest cameras that you will have, the aperture is only 10 millimeters, something of that order, maybe 20 millimeters if it's a very large lens. So this distance here is very short, right? It's only measured in tens of millimeters. It's very close to the front of the camera. So if you move the sensor away just by a small distance, you bring the focal plane very close. If you move it even slightly further, this diagram may not look this way, but this distance here and to this point are meant to be equal distances from the lens. Okay, you end up with something that is equidistant from the 2 points, so sort of symmetric. I'll come back to that looking later. If you move it much further from the sensor, because of the nonlinearity of this equation, the object distance here continues to get closer and closer to this focal point, but it moves very slowly now. Can you see how this is converging and starting to change very slowly towards the focal point as this distance here is getting larger? In fact, you need to move the focal plane to sort of infinitely far away, right? Actually, mathematically, exactly infinitely far away in order to be able to focus on objects that are at the focal point of the lens in the real world. The final slide here is that if you actually try to move to focusing on something that's closer than the focal point, you can't put the lens the sensor rather at any distance that will actually form a real image of that. So it'll always be blurry. Okay, you can't form a sharp picture of that. Okay. Anyway, so this is sort of gives you a flavor for some of the nonlinearity, and the part that isn't shown here because it's hard to show those convergence distances on this sheet of paper is between these two here. This represents focusing from infinity all the way through to a few centimeters or so from the front of the camera. A few comments that I made already. Z sub I and Z sub O are called conjugate points. Okay, I think I described this. This case here, Z sub I to Z sub O is called one-to-one macro. I'll come back to that in a slide later. And for Z sub O, one other comment I didn't make is that for Z sub I greater than Z sub O, that is the distance here being greater than the distance over here, the image that we get on the sensor is going to look larger than the object itself. That is, this thing is acting kind of like a magnifying glass, or in the extreme case, like a microscope. Okay. And okay, so that's the last comment there. Let me get into a bit more of the mathematical details around magnification, which is a topic that I touched on just on the previous slide. Okay, so what is the magnification? When you take a photo, you often want to know, okay, relative to the size of that object in the world, how big is the image that appeared on my sensor? Okay, you can formalize that as the magnification. So the size of the object versus the size on the image plane. Let's say you put the sensor in this case at Z sub I. The magnification then would be just H sub I divided by H sub O, which by similar triangles will be Z sub I over Z sub O. Let me just transfer that and give you an example on this slide. So here's the first magnification example. Let's say we focus again at infinity or very, very far away. This is a really common photo that we take, right? You just point it at a sunset or a mountain in the distance and you take a picture. In this case, the magnification, your intuition should be that it should be really small, okay, from this definition. It's a huge mountain, and it appears inside your sensor, which is a small thing. It's only millimeters across, okay, so a huge thing getting imaged onto a small thing, the magnification in that case is going to be a very small number. So Z sub O is close to infinity, miles away the mountain. Z sub I is going to be equal to F from this thin lens equation. I walked you through that example earlier. This means the sensor is at the focal point, and the magnification being Z sub I over Z sub O is going to be close to 0. Okay. Let's look at another example where you do what's called macro photography. This is like taking pictures of very tiny objects. Okay, not just like food photography that's getting towards macro, but almost taking pictures of like tiny insects or like maybe even tiny jewels, things like this. Okay, this is this is focusing at one-to-one macro. Macro photography means taking pictures at high magnification for camera photography. One-to-one just means like whatever appears in 1 unit size on the object is going to appear in the same unit size on the sensor surface, as you can see depicted here. Okay, so the size of the object over there appears the same size here. In this case, so what configuration do we need to achieve a magnification of 1? So this one-to-one macro case, it turns out that you can reason this through from the magnification being Z sub I over Z sub O. We need Z sub I to be equal to Z sub O to be unit magnification. And so from the thin lens equation, Z sub I and Z sub O need to be half F. Okay, so that the sum of them is going to be equal to 1 over F. And so in one-to-one imaging, we end up putting the sensor at a pretty large distance, twice the focal length. We need to push it back from the sensor to twice the distance of the focal length. And we have to bring the object until it's positioned very close to the camera, also at a distance that's equal to twice the focal length. When we do this, again, what happens? The object, how do I say this? If the sensor is, say, a full frame sensor I talked to you last lecture about, if it's 36 millimeters wide, the sensor, then the object will that is 36 millimeters wide in the world will fill the frame. Okay, will fill the sensor frame. A question, good question came up here. In a real camera, are we moving the lens or the sensor? Great question. In a real camera, you'll be moving, if it will be moving the lens. In fact, we'll be moving some lens elements inside a compound lens. The net effect of it optically, though, will be to change the distance between the lens and the sensor. Okay, so that's the way to sort of think about it. It'll be optically equivalent. And so you can look at this picture here of this damselfly, which was taken with a one-to-one macro lens, and deduce that the size of this damselfly is actually really small. Okay, it's about 30 millimeters or something across. I want to show you a few other pictures just of some of these conjugate depths. Let me pause for 1 second and see. Got a question. So the focal length of the lens can change in a real camera. Yeah, great question. Actually, I want to emphasize something about this. So in these diagrams I'm showing you up to this point, I want to be really clear. The focal length, okay, so actually the question was stated in a way that is really helpful to clarify the terminology. The question was, so focal of the lens can change in real cameras. And I want to tease that apart, okay? Focal what? So the focal point or the focal length of the lens in all the examples I've shown you up to this point is fixed for these lenses, okay? It's a fixed dot here, and it's not changing as we vary the position of the sensor. What is changing is the focus in the photograph of the camera that's using this lens. And how that is working is that we're changing only the separation between the lens and the sensor, okay? The position of this blue plane. The focal length and the focal point of the lens is not changing. So that's sort of thing one to know. Okay, all of these things we're doing, which are focusing at different depths, do not involve changing the optics of the lens necessarily, only the relative distance between the sensor and the lens. Now, it is true that there are lenses, of course, where you can change the focal length, change the focal point. Those are called zoom lenses. So zoom lenses are a special class of lenses where we can turn a ring, for example, on the lens that mechanically will reshift in a nonlinear way some of the multiple elements inside the compound lens that, because of optical engineering of that lens, causes the focal length of the lens, which is the distance between the focal plane of that lens and the convergence point that it brings parallel rays to, it'll increase and decrease that focal length. It will literally change the distance in millimeters of this distance here between the lens and the focal point. That's a zoom lens, okay? So thanks for that question, really good one. All the examples that I'm showing you here today, I think, are not going to talk about zoom lenses. So we're going to assume that for any lens I show you, the focal point is a fixed property of that lens. I want to show you, just to give you a bit more intuition about what's going on here for the shape of these objects that are in 3D that are taking place in the world. Here I'm showing you the same object in the world, a red sphere, okay, as a little cartoon. And I'm showing you the image of that object as a three-dimensional thing inside the camera on the right-hand side. Nothing special going on here. All we're doing is taking every point over that red circle and computing through the thin lens equation where it will appear on the right-hand side, and then drawing all of them. And what you'll notice right away is that in general, a circle on the left-hand side or a sphere is being mapped to like an oval, right? An oval, it's stretched along the optical axis or compressed. You'll notice that when the circle is further than or quite far from the focal plane, that oval inside the camera is squashed, okay, it's narrow. And when it's at this distance, which you might recognize now as one-to-one macro, a circle is mapped to a circle. But when the circle in the world gets closer to the focal point, actually on the right-hand side, you can see it, it's quite dramatic. The image of that object gets spread really out in depth. Now, what can you make of this? Right away, you can sort of deduce that if you are going to create a camera with this and you have a sensor plane, then you can only put it at one geometric plane, right? Because it's a CMOS sensor that's rigid. If you put it here, you could expect that, it's going to be able to capture maybe the whole ball in focus at the same time, the whole depth of the ball in focus at the same time. If you try to place the sensor somewhere in here, you're going to, because the sensor plane is flat, you're going to have to pick which plane of this ball to bring into focus. Okay, and not the whole ball will be in focus at the same time. This is a true property. It's one of the nonlinear properties of focusing and depth of field of of lenses, okay, that falls out just purely from the thin lens equation and, from Gaussian thin lens model and then the thin lens equation that we've derived. It brings about these effects that I just shown you here. And you can intuitively feel already that when you focus on closer objects in the world, it's going to be a much thinner plane in the world that's going to be in focus, and other stuff is going to be defocused. We're going to analyze all of that and deduce exactly how out of focus it's going to be. But the intuition here, I think, is really important. And if you take away this intuition, you will understand cameras, I think, intuitively in the macro scale the best, or in the macroscopic scale the best. If you focus at infinity or close to the focal, put your sensor close to the focal point, a really large plane, large range of depths in the world is going to end up being in focus. Okay, so we'll look at the mathematics of that and equations for that as we go. Got a question here. Would you have to change the sensor length or distance only on the right-hand side, or also the object's distance from the lens on the left-hand side? Yeah, good question. You kind of always have to change them in concert, okay? So this distance here is matching to this distance, or quote unquote conjugate, right? That term again, to this distance over here. So you have to get them matched through the thin lens equation for the specific focal length f of this lens. In general, of course, for the camera, what you do in practice is that if you know how this works, right? You use autofocus. So you put your camera at some distance from the thing you're trying to take a photo of, and then you either tap on the screen, or if you have a smartphone, it might just automatically do it for you. It focuses on that lens, and what it's doing is it's physically moving the distance between the lens and the sensor, moving that sensor plane until it finds that sensor plane exactly here, so that it's focused on the object that you care in the world. Okay, so pragmatically, that's what's happening in a real camera. Okay, let's keep going. The next thing I want to share with you is how we can analyze, completely calculate the defocus blur that we expect in photographs. Now, I think we've all noticed this effect before. Let's really get into the details of it here. That if you take a photograph in the world, then things that are further than the plane of focus are going to be blurry to some degree, and things that are closer than that focus plane, they're going to be blurry too. This is a pretty prominent example of that because it's taken with a large camera. The same effect happens with our smartphones, but it's a smaller effect for geometric reasons that we'll derive today, quantitatively. But this is just taken with a large camera, and exactly the same effects are happening even in your smartphone. So how big is the defocus blur for any particular object at any particular depth? That's the question that we're going to look at here. Okay, and a way to quantify that is called the circle of confusion. So what's the circle of confusion? Here is a circle here, okay, in the foreground that I've overlaid. This circle is due to, what is this scene? It's a picture of a baby standing in, these are some Christmas trees, okay? It's in some kind of hotel foyer. So there's a Christmas tree in the background, there's a Christmas tree in the foreground. This is one of the Christmas lights on that Christmas tree, okay? And you can see that it's blurred out, that point of light from that little bulb has blurred out to form a circle here. So that one point in the world from that Christmas light is now on the sensor turned into a circle of illumination. We can think of the diameter of that circle, or we can think of the circle, we'll call that the circle of confusion, the blur circle, okay? And the diameter of it will be a figure of merit of how blurry it is. Here's another circle of confusion in the background. This one is corresponding to a Christmas light, right, on the tree that's further away. That's also blurring out into a circle that you can see here. So this is due to defocus point lights that are further than the plane of focus. So the size of the blur kernel, or the size of the circle of confusion here, is going to depend on the depth from the distance from the focal plane in the world. And we're going to derive exactly what that relationship is, okay? And a couple of comments, though, before I go on to that is like, okay, I'm showing you a special scene here where you can see these circles of confusion as perfect circles, okay? This doesn't happen in most every photograph that you'll see. You'll always see this blur for objects that are closer and further, but they may not appear like perfect circles here. Here we see the blur kernel itself. Okay, the blur kernel is a circle. It's due to the circular aperture of the lens. Why is that? It's because that point of light is going through the lens, and then as we'll see geometrically later, it's actually diverging through a point inside the camera and splatting onto the sensor plane to create this puddle of light. And the puddle happens to be a perfect circle because of the circular iris, or the circular aperture of the lens. Now, you don't see that in many cases. For example, over here, you'll notice that you see green, right? It's a blurry green. You don't see the needles of the Christmas tree. You just see a blur green of the tree. It's because there's many points of similarly colored green there, and they're all blurring together with a convolution kernel that is the same size here as this depth over here. So the convolution kernel size is over here. Similarly, the convolution kernel size for things in the background are this size over here, corresponding to that circle over there. Okay. So circular confusion. We saw it visually. Okay, so that's what we're trying. That's the idea. Closer and further things are going to blur out. How much are they going to blur out on our sensor plane? That's what I want to calculate next. Unfortunately, it's really, like the geometry is pretty much as trivial as the thin lens equation derivation. It just is going to use similar triangles and a little bit of algebra. Okay, so let's do it. There's a little bit of the geometric construction here to look at and understand. So let me just walk through it again. Let me start with the sensor plane on the right-hand side. Okay, so the blue thing here is the sensor plane. So with this sensor plane at this specific distance, which I'll call Z sub S, S for sensor, at this specific separation from the lens, I want you to recognize that that is a camera that is focused at a specific depth in the world. Okay. The lens and the sensor is a camera, and then whenever it's positioned at a specific separation, that camera is focused at a specific depth in the world. Which depth in the world? In this case, I've drawn it here for you. Here's the focal plane. This focal plane is conjugate to the sensor plane. So I've drawn it here as Z sub S prime. So Z sub S and Z sub S prime are matching distances under the thin lens equation. Okay, so if we put an object there, we would see a sharp picture of it. But in this scene that we have here, what we're going to do is analyze having an object that's not at the focal plane. It's not in focus. Let's do the one for the Christmas tree light that's further. Okay, so here's the object in the world that we're trying to analyze what its circular confusion is. So I assume this is the Christmas light as an example. And it's at a distance Z sub O to the lens. We want to know, okay, what size of circular confusion is it going to be on the sensor surface? Just look ahead. That size is going to be the capital C thing over here. Okay, so how did that happen? The rays of light come out of that object. They refract through this lens. And where do they go? We know they're going to converge through this point over here, which I've labeled the image plane. This image plane is conjugate to the object plane. Okay, so it's the same terminology I had before, Z sub I and Z sub O for this object and image. It's not the image that appears on the sensor. Okay, it's not the photograph that we get. It goes through this a point on here at the distance Z sub I. And we know how to calculate that from the thin lens equation. These rays of light refract through this lens, rather. They all converge on this point in the image here. But think about it. That's a point that's sitting inside the camera body between the sensor and the lens. It's in the middle of air, okay? So each of these rays of light refracts and passes through this point over here. And they just keep going because it's just clear air. So the rays just keep going through, and then they land on the sensor plane at some distance that we can easily visualize by just tracing through and using our kind of ray tracing intuition, okay? So in other words, all the rays of light emanate from here in a cone of rays out from the object. That cone of rays is bent by the lens, passes perfectly through the image here as a converging cone, and then they emanate, continue through that focal point there as a now diverging cone of light, and it strikes the sensor surface. And the cone is going to land on the sensor surface as a circle. And the circle is going to have a diameter C. Okay, that's the geometric construction here. Okay, if you followed that geometric description, then the derivation of this C is really simple, okay? Because all we need to do is relate it through similar triangles. C here is similar to A as this distance here. D prime here is to Z sub I here, okay? I did that similar triangle slightly differently, but hopefully you can see that those relationships are a simple relationship here. C over A equals D prime over Z sub I. And D prime is just a helper variable for this gap here. That is just equal to Z sub I minus Z sub I. Okay, so what's it saying? It's saying that the distance from the sensor through the lens to the lens minus the distance of the image to the lens divided by the distance of the distance of the image to the lens is going to give us C over A. And from that, we can calculate C. Okay, let's look at an example. Okay, let's go back to this picture of this baby with the Christmas trees. We got our equation now. I simplified it to give us explicitly C and the aperture A and all the rest of that. This is taken with this lens here. Okay, it's a 50 millimeter f2 lens. Remind you of that terminology last time. 50 millimeters is the focal length. F2 is the numerical aperture of the lens, which, as a reminder, is the focal length divided by the diameter of the opening in the lens. The diameter in the lens is what? It's A in this diagram over here. Okay, so F over A equals 2. This was taken with a full frame sensor, 36 by 24 millimeters. The focus in this case is, it's the distance from the lens focal plane to the kid here. Okay, that's about 1 meter. Okay. The background, the Christmas tree in the background is about 10 meters away. And the foreground, in this case, the light on the Christmas tree in the foreground is about a foot away. Okay, I call it 30 centimeters or so. So those are our numbers. So then all we do is we plug it in. Okay, A is equal to 50 millimeters divided by 2 because it's F2 lens. That means A is 25 millimeters. Z sub S is, if you haven't seen this kind of equation before, you can kind of take note. Okay, this is interesting. Z sub S, the distance between the sensor and this plane over here to focus on the child that is 1 meter away. 1 meter is 1,000 millimeters, right? So it's going to be 1 divided by 1 over F minus 1 over Z sub O. That's 1 over 50 minus 1 over 1,000. You can chug that kind of math. It turns out to be 52.63 millimeters. That's interesting practically because think about it. So the distance here, okay, D prime, that is for a 50 millimeter lens, which has a focal length roughly, okay, call it that far away, to focus 1 meter away in the world, okay, so like maybe your arm's length or a bit further, is 2 millimeters. You move it 2 millimeters in order to focus at that kid in the world. Okay, so take that as a fact. The background, calculate Z sub I. Oh, what is the image depth at which that appears? 10 meters away. You can chug this 1 over 50 divided by 10 meters, which is 1 over 10,000 millimeters. That's 50.25 millimeters. Okay, then you can just plug the rest of this in. C is equal to what? It ends up being 1.18 millimeters. This is a cartoon over here. C is really large compared to the sensor plane. Remember, what's the size of this sensor? 36 by 24 millimeters, okay? So 1.18 millimeters is not as big as this cartoon. It's the size of that circle in the background. You can relate it to like if you had a 4K sensor and you put it up on a 4K TV, okay, that'd be like 130 pixels across that circle of confusion. You can calculate for the foreground. It's the same math, just with the numbers for the foreground instead. End up with a 3.07 millimeter circle of confusion. Okay, 338 pixels on a 4K TV. Okay, I went through some numbers tied to a specific camera. Didn't mean to belabor the point, but show you this is how you can crank out all the numbers and how some of the specifics look. Okay, the numbers end up being pretty small distances away from the focal plane for focusing at really typical distances in photography. This is the nature of math and the kind of numbers in the real world for real cameras. Okay, is C the diameter? Yes, C is the diameter of the circle of confusion. A is the diameter of the opening in the lens. Which formula is used for the Z sub S? Oh, great question. Z sub S here. This is just the thin lens equation 2. Okay. Oh, yeah, very good question. Let me walk you through this. Okay. I said that we focus on the baby and the baby is 1 meter away. So that means Z sub S prime here, this distance here, is 1 meter or 1,000 millimeters. So if 1 over Z sub S plus 1 over Z sub S prime equals 1 over F, that's the thin lens equation, then we can solve for Z sub S here. Okay, with this. Good question. Thank you. Okay, lens, what have we got on this slide? Let me open this up. Okay, the lens's F number versus the F number for the photograph. Oh, this is a sort of an important point to sort of say. For, sort of professional or serious photographer cameras, there's sort of a difference between the F number that's printed on the lens physically when you go buy it versus the F number of the photo. Okay. And that's for a very simple reason. It's just that the lens has a controllable iris. I described this a bit last lecture, so that even though you have one physical lens that you're going to click onto your camera, you can actually set the aperture, by turning a ring sometimes or setting the controls digitally on your camera to turn the aperture, that is the metallic sort of leaves inside the aperture, inside the lens rather, to close the size of that opening down. If you open it all the way up for an f1.4 lens, then you'd get the maximum size aperture. you get the blurriest, closer for, the blurriest photos for out of focus regions. If you close it down to a small aperture, then you'll get a larger region of the world that's in focus. So the F number for the photograph corresponds to the lens setting at the moment you took that photograph, obviously. The F number for the lens is the maximum possible F number that it was manufactured to support. Okay, so good to know. Let me show you just a simple examples of F number calculations. Okay, so here's a simple lens here, say the diameter here being 50 millimeters, the focal length being 100 millimeters. That's an F2 lens, 100 divided by 50, okay? If you had a 100 millimeter diameter, but you had a focal length of 200 millimeters, remember that this is like a telephoto lens, this is still an F2 lens, okay? 200 divided by 100. If you had the same 100 millimeter diameter and a 400 millimeter focal length, this is an extreme telephoto lens, something that like a sports photographer that's shooting at a very large distance might use. This is an F4 lens, 400 divided by 100. Okay, this would be a much darker lens. It will make gather a lot less light than this lens. These two lenses will gather the same irradiance onto the sensor surface because it's related to the F number, as we discussed last time when I talked about exposure. And just to anchor this again, okay, f2.8, large lens opening, blurry background in this picture. You can use the same lens. Stop it down is the term, okay, to close the iris down. That's the terminology is sometimes used to stop it down to f16. Same camera, same lens, but now, decrease pupil size and you get the blur circle in the background being smaller. Why is that? Well, remember, C is proportional to A. A was the diameter of the lens opening. And of course, you can see the lens opening is smaller here. And the number here is f16, right? So N is 16. A, the diameter of the lens is just equal to F over the F number, N, okay? So that's just the way that that's just all terminology explaining how to use this F number. If you haven't seen that before, that might take a little bit of just looking at to get used to what an F number definition is and how it shows up in some of these equations. What ways are there, if any, to change the shape of the circle of confusion? Oh, great question. And I see Jessica as a response to that, to Aiden's question, probably the shape of the aperture. That's exactly right. And you can put a pattern over the lens for some types of lenses and change the shape of confusion. I'll show an example of that later in lecture, actually. I'll show you a photo. Okay, exposure trade-offs, depth of field versus motion blur. This is a big topic. Okay, exposure trade-offs in photography, that is, we're going to trade off the depth of field, which is how much of the depths in the world look sharp in the photo we get, versus how much motion blur we get. Now, why does this show up? I mentioned this last time in exposures. I said for the same exposure, the exposure was the net irradiance, right? The exposure was the total energy, if you will, per pixel captured in the photograph we get. That's set by whatever value we want. We set an exposure. The exposure is the same in these three photos. You can see that this woman here has the same brightness, okay, approximately speaking, in these three photos. But we can get it in different ways, as I mentioned last time. We can have a large lens aperture, f4, for a short shutter duration, 125th of a second, or we can have a medium exposure, a medium aperture with a medium length exposure, or we can have a small aperture, f32, with a long exposure. All of these have with a long shutter duration. All of these have the same exposure level, but they have different trade-offs between the the lens aperture size and then the duration at which we have to open the shutter. The effect of that, as you can see in this picture, is that for large apertures, we have a shallow depth of field. That is, the background is blurry here, right? And even though the woman's in focus. But since they have a short shutter duration, her hand is, even though she's waving in all these photos just like this, it's sharp here. And in the other example, because we have a small lens aperture, we have large depth of field, the background's in focus at the same time, but then we need a longer shutter duration, half second. And so over that shutter duration, her hand is motion blurred out. Okay, this trade-off occurs every time we take a photo with any camera system. You may not be making this trade-off. It may be inside the autofocus or the auto exposure algorithm that's built into the camera system, for example, in your smartphone, but somewhere this engineering trade-off decision needs to be made, okay? On the right image, are we getting more depth becoming sharp, or is it just the blur circle is smaller? Both. The blur circle, the circle of confusion in the background, is large on the left image and it's small on the right image. And because of that, in fact, the blur circle is smaller at all depths in the right image compared to the first image. Because of that, we get a sharper looking image at a larger range of depths in the world on the right-hand image. The depth of field, I'll talk about this a bit more later, but the depth of field is the range of depths in the world that look sharp, okay? This has a large depth of field on the right-hand side. This over here on the left-hand side has a shallow or a small depth of field. Someone has a good question. Can we solve this trade-off by changing the ISO? Yes, that's another variable here that can trade off between here, not without its own trade-offs. As we know, increasing the ISO, which is the gain or amplification level from the sensor to the digital file that we get, that will amplify noise inevitably. So you get a trade-off in noise. But you're right, that's a third variable in the mix here for setting the exposure level. I discussed that last time, and I won't go further into it today. Okay. Now, I want to point out also, it may already be apparent to you in these photographs here, but here's a more dramatic example that makes this point. A shallow depth of field is not necessarily a bad thing. In fact, many times it's a highly prized thing in photography to be able to create a shallow depth of field because you can isolate a subject of interest and make it more prominent. So here are two photos of exactly the same scene, one with a large lens aperture and one with a small one. And you can see how much the large lens aperture is causing our gaze when you look at the scene to end up focused on the lily in the foreground and then these three buds here, compared to on the right-hand side where those are sort of competing with all the detail, the visual detail in the background, and they don't stand out as much. Okay, so shallow depth of field can, for certain kinds of photographs, create a stronger image. Now, does that mean that, well, motion blur is the problem, so we should try to get rid of that? Well, not necessarily either. Motion blur can help to tell the story in photography. We've all seen examples of this, but let me show you one here. Okay, so here's a boy being kind of overrun with pigeons after feeding them. And the fact that there's a longer exposure here relative to the motion of the pigeons so that their flapping wings have blurred out helps to give a sense of the action and the sort of, velocity of the birds in this scene, okay? Is this why my webcam blurs the background because you want to create a stronger image? Yeah, that's a great question. Yeah, really good question that Kyle asked. Exactly right. So this, the webcam that I use actually ends up. This is a large aperture interchangeable lens camera that I've hooked up to my laptop, and so yeah, it has a shallow depth of field, and you'll notice certain things. So for example, if I move closer, it has autofocus, so now it's focused more on me. Do you notice the background's more blurry now? It's even more. So when I move closer, you see how it's even more blurry in the background. You might also notice now it's focused on my eye, but my ear is out of focus. You notice that? If I move back, which I pointed out to you that would happen if for things that are closer to lenses, which happens with every lens, is sort of intrinsic to the way that lenses behave. If we move backwards a little bit, you might notice that it's still focused on my eye, but my ear is a little bit less out of focus, okay? It's more within the depth of field as I move backwards, and the background is less blurry too, okay? But yeah, it creates a better separation from the background. This is a 50 millimeter lens for the record, the one that I'm using here. Okay, depth of field. I already described depth of field. We had a question about it in the chat. And so again, the depth of field is the range of depths in the world that are rendered with acceptable sharpness in the image that we get, okay? For a large lens aperture opening, we have a shallower depth of field, right? The range of depths that is sharp, critically sharp is centered on the man here. For a small aperture opening, the depth of field increases. Now it extends from the man evidently all the way to this building that's far off in the background. Okay, so think about it. This depth of field is probably measured in feet or meters. This one here is measured in tens or hundreds of meters. In fact, it can very easily run to kilometers, as we'll see. Okay. Again, non-linearly because of the thin lens equation. Let's work through that a bit and see what's happening. So again, this definition here is a bit of subtlety I want to point out. It's the depth of field is the range of object depths that are rendered with acceptable sharpness in the image that we get. You could actually spend quite a bit of time thinking about this and analyzing that definition, which is subtle for for very good reasons and important reasons. Let me just try to hint at some of the reasons for that and the subtleties in digging into it a little bit here. Okay, render with acceptable sharpness is a way of relating the depth of field in the world to the permissible circle of confusion in the photograph that we get. For any particular point. Okay, so if we're trying to say, hey, this depth in the world, is it going to be acceptably sharp? One way to think about that is to say, hey, is its circle of confusion acceptably small? If it's small enough, then we won't notice it. Okay, so recognize again, for some point out in the world, it's refracting through the lens, geometrically passing through the ideal focal point here. But before this cone of rays arrives there, and after it diverges from that point, there will be a range of depths here that's annotated as called the depth of focus. Can you see that here? Okay, so this total distance from this little circle here to this circle here, this depth here is the depth of focus. That where everywhere in here, the circle of confusion is smaller than what's labeled here as the permissible circle of confusion. So there's a bit going on there. Let's talk about it. If you put the sensor exactly at the focal point, okay, then it's going to be sharp. Okay, but if you're a little bit closer or further than that, then it might still be, in the depth of field if it's within this depth of focus, within the place where the circle of confusion is sufficiently small. But what's sufficiently small? What's a permissible circle of confusion? So let's talk about that just a little bit. What I write here, it depends on how you're going to use the photograph, I think is the most important high-level point to make. For example, if you're going to print it on a wall and allow people to walk straight up to it and really critically examine it, then even a tiny little circle of confusion on the sensor surface after magnified into a huge poster or wall size might look a little bit blurry. People might be able to tell, okay? So for printed photographs, a very common metric of acceptable sharpness back in the days of 35 millimeter film was something like 0.025 millimeters on the negative. The negative was 36 by 24 millimeters across. That was 25 microns, okay? So what does that mean? For digital image sensors, maybe a bit easier to reason about. Maybe a reasonable definition is the permissible circle of confusion being related to 1 pixel size. I mean, if the blur is smaller than 1 pixel size, we maybe would never see it, right? Okay, it seems reasonable to think about. So 1 pixel in a smartphone is, a decent number, is like 1.4 microns, for example. For a large camera, it might be like 4, 5, 6 microns, something like that. So that's another reasonable example. However, what if you're taking the picture and then you just end up, I don't know, sharing it on the internet in a thumbnail form, okay? And people just only ever see it, I don't know, like as one of the thumbnails in a gallery on social media or something like that. Well, think about that a little bit. If the person ends up looking at it at web resolution or on a small size on a phone, they're going to have a hard time telling if the circle of confusion is even pretty large. So I think from this little bit, I don't want to belabor this point, but I think you're getting the idea that based on the usage of where someone's going to look at that photo, the permissible circle of confusion for reasoning about the depth of field is going to change. Okay, the smaller the photo, the lower res the photo, actually, the larger the permissible circle of confusion, and the larger the range of depths in the world that is going to appear like it's sharp. Okay, so all right, you could think about that more, and for any particular applications that come up where you have to think about focus and whether you'll have an acceptable, blurriness or not, I encourage you to think about that. I'm going to leave that at this point. Let's go through, this is going to be, I apologize, a pretty math-heavy slide with a lot of algebra on it. I'm not going to expect you to remember any of these equations or even to rederive these equations, which are algebraically a little bit more complicated, significantly more complicated than the derivation of a circle of confusion or of the thin lens equation. But I want to show it to you because actually there's not a lot going on here to calculate the depth of field or the depth of focus in the camera completely analytically. And it all just flows again from the thin lens equation that we've already covered today, and then some algebra, which ends up being more messy. Let me show it to you. Okay, so again, it's going to start from the geometric construction. And if you remember one thing on this slide, it will be to look at this geometric construction and understand what it's showing, okay, and why the depth of focus is defined geometrically, why it's valid to define the depth of focus in this way and the depth of field, and to recognize the lack of symmetry. Okay, this is not like a perfect diamond here. It's more like a kite shape, and the kite shape over here is in the other way. That is because of the thin lens equation and its nonlinearity. Anyway, let's recognize that in this distance here, the circle confusion between these 2 points, if we say C is the maximum permissible circle confusion size for an acceptable sharpness, then the depth of focus that we saw in the previous slide, this is the range of depths where we could put the sensor, okay, and still get a sharp picture of that depth in the world. And it's going to be this big. And the depth of field is just the range of depths that is conjugate to the depth of focus range of depths here. Again, conjugate just means that the depths there are related to the depths on the inside of the camera through the thin lens equation, okay, through focusing. Okay, so if you look at this geometric construction, okay, starting from the circle confusion and deducing the range of depths here by this construction here that would result in that circle confusion, and then recognizing that we're just going to take each of these depths here and flip it around through the thin lens equation to look into the world, then everything else will be algebra. And I'm going to walk you through it very briskly without dwelling on the details. Let me just do and note the definitions here. We have F, which is the focal length again, right? As we always do. What I've defined here are 3 quantities inside the camera with little d's that have corresponding depths in the world with capital D's. Those are for F, S, and N. For far, because this is the far depth in the world of here, a capital D sub F. S for sensor, because this is the conjugate distance to the sensor plane. And capital N, because it's the near plane, okay? So F, S, and N. This is the far point, the near point, and the sensor depth inside this geometric diagram, and the corresponding distances inside the camera. If we have that, then let me think about this for a second. Okay, this is from similar triangles. We can write down these equations over here inside the camera. We also have the definition of the numerical aperture of this camera, which is little f over a. And then we have these 3 equations here, which are just 3 applications of the thin lens equation, right? It's just 1 over z sub o plus 1 over z sub I equals 1 over f for each of these 3 pairs of distances here. And then after that, what are we trying to do here? We're trying to calculate the depth of field. The depth of field is what? It's it's the range of depths in the world that will be rendered acceptably sharp according to the circle of confusion that we've chosen. So that range of depths in the world is capital D sub F minus capital D sub N here. And we're going to get it as a function of the numerical aperture of the lens, or the aperture size here. In this case, I've chosen to use the F number of the lens, or the aperture size. I've chosen to use the F number of the lens, capital N here. And it's going to depend on the sensor depth, and it's going to depend on the circle of confusion that we find permissible, capital C here. You can chug all of these to produce these 2 equations here. It's a little algebraically annoying. Okay, so it's not interesting to look at anyway. I've just written the result down here. Okay, but I want you to understand this geometric construction, that these are all very, these assumptions here are all geometrically very straightforward from this diagram, and the rest is algebra. I see a question here. How do we know where A is? Is it given to us so that we can calculate C? A is a property of the lens. Okay, or of the lens setting for the photograph that we're thinking of calculating this depth of field for. So A here is just the geometric diameter of the opening in the lens, okay? And from that, actually C in this case is separate. C is the circle of confusion that we're choosing. We say that's permissible sharpness. I told you that sort of depends. I gave you a couple of examples of how you could choose one, but also noted that it might depend on your usage, and you'd have to think a little bit about it critically. But from that, you can choose a C that you find permissible, and then the rest of it follows from this geometry and algebra. Okay, thanks for that question. Okay. Oh, and then I had a little diagram here. I realized that these unfortunately don't work anymore. I've been trying for a little while to look for alternate interactive demos for these, and unfortunately, I haven't found a good one. I tried quite a bit to find one, so I regret that. Otherwise, this is something you can just work interactively and kind of drag around to see as you change the proximity of the sensor to the focal plane, how the depth of field in the world changes. Let me just describe to you what happens. As you move the sensor close to the focal plane, this diamond over here moves closer and closer to infinity, but it also becomes much, 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 much larger. This kite shape over here stretches out. And by the time you get close enough to the focal plane here for this part of this kite structure, the front part of it, to touch the focal plane, this diamond here will have touched infinity. Okay, so infinity will be sharp, and it will extend all the way through into the closest point in the world that's brought to focus by something called the hyperfocal distance in the world. It's a large distance. If you try focusing on infinity with almost any camera, you'll notice that a huge depth of range in the world is focused from infinity through to pretty close to where the camera is. Well, why are both the terms the same? Isn't the depth of field non-zero? They're not the same. Really good question. Yeah, okay. There's a minus here and there's a plus here. And I haven't looked at these equations for a long time since I derived them. I think, yeah, that turns out to be the only difference. The algebra was not very memorable. Didn't end up in a place that was particularly easy to remember. So you can look it up if you ever need to. But you can derive it from scratch if you're a bit of a bludgeon for algebra. Okay, let me switch gears a little bit and touch on a pretty fun topic: ray tracing ideal thin lenses. Okay, I touched on this in the past. I said, hey, we are writing ray tracers. We talk about materials that are realistic, lighting functions that are realistic. Here's a picture that had sort of realistic camera effects, like this blurriness in the background. You can see there's a depth of field here that extends over some of the objects in the foreground. The background is slightly out of this depth of field. Okay, and similar in this kind of photograph, this is out of the depth of field in the background there. Here's another example, a little bit more, like a clinical, okay, like a test scene for computer graphics. These dinosaurs that these dragon statues that scans of these dragon statues that we've been using in some of the scenes that we provide you. And you can note here that it's focused on this, actually just the back of this red dragon, and everything closer and further is out of the depth of field. And you can see how extremely defocused it gets as it gets to the front of this line of dragons here. How do we render something like this in our ray tracers? And the good news is that it's actually a really simple algorithm. It didn't come easily in the computer graphics community theoretically. It took quite a while for people to hit on this, as a way to add it to ray tracers. Let me walk you through it, okay? It's really neat how simply it works out at the end of the day, and hopefully this flows from some of the intuition from the thin lens equation and being able to draw the key rays through the Gauss ray diagram that I've been teaching you today. Let me show you exactly how it happens. Okay, so here's a little cartoon for a scene that we want to render. It's got, in this case, the scene is a couple of bunnies in the world. Okay, we have a lens and we have a sensor inside the camera. Okay, so we want to make the picture corresponding to this scene. So what do? So the setup before we start tracing rays is we have to do a few things. We have to decide, choose the sensor size, okay? As we talked about last lecture, that's going to define the field of view. We have to choose the lens focal length. That's also going to affect the field of view, and it's going to affect the depth of field, right? How blurry things are in the world compared to where they are to the focal plane in the world. And we have to choose the aperture size, which will also affect the level of blurriness away from the focal plane. So you're going to choose all those physical parameters. What's a good way to do that? A good way is to, you can start from some physical lens parameters in the world. You could, for example, go online, find a picture on a photography website, look up and say, hey, this kind of has the kind of depth of field for the size of objects that I'm thinking of. You can look at the lens settings that you can often find on photography websites. Say, oh, this was the focal length. This was the F number of this lens. This was the size of the sensor in the camera that was used. Okay, so that's one way you can do it. Then you got to choose what's in focus. That's the depth of the object in the world of interest. In this case, I've already labeled it. we're going to focus on the closer bunny in this cartoon. Okay, so this is the distance z sub o here. Then we got to calculate the corresponding z sub I, okay, which we do trivially from the thin lens equation that we got. So then we take the z sub o that we care about and the position of the camera that we've chosen, and we calculate z sub I, and we space the sensor at that distance. That's crucial so that when we render this picture, we're actually going to get a photo that's focused on what we care about. Okay, so that's the setup. Then we go about rendering, okay? So to compute the value of a pixel at position x prime on the sensor, which is a pixel, right, in the final image that we're going to get. And we're going to do this by Monte Carlo ray tracing. How do we, path tracing? What do we do? Okay, so the first thing that we do is we select a random point on this x prime lens plane over here. I've shown you two examples of them, but let's use the label one here, which is x prime up here. Okay, so we just choose a random position on the aperture. Now, the next thing is we can notice that the rays pass from point x prime on the image plane through x double prime over here. Okay, that would be the contribution of a ray of light from the world refracting through the lens onto the pixel that we care about in this image. And we can note, we have to use deduction of all the things we've talked about in class today. We can note that we also know exactly where this ray comes from in the world, its trajectory through x double prime here, because by the fact that we've chosen z sub I to be conjugate to z sub o, or focused on z sub o here, and because we can draw this chief ray here from x prime through the center of the lens, the pinhole point, through into the world onto this z sub o plane, we can find this point x triple prime here. And from a thin lens equation, or the thin lens model, we know that this ray here, this ray of light that passes through x prime there has to also pass through x triple prime over here. So each ray passing through each ray that we choose x double prime here also has to pass through the conjugate point x triple prime on the plane of focus z sub o in the world. And I described already, we can determine the exact location of x triple prime from the Gauss ray diagram here. Okay, so we just trace the ray from x double prime into the world towards x triple prime, and we use path tracing, for example. We estimate the radiance that would pass back from the scene along this ray, for example, by using path tracing with Russian roulette and all the rest of it. And I said we choose a random point x double prime here, right? In path tracing, as you know, we trace many rays that pass through this pixel here, tens, if not hundreds, or even thousands of rays. So for each one of those rays, we can choose a different x double prime over this lens plane. Maybe you can see what that's going to be doing in a Monte Carlo integration sense. What it's going to be doing, right, is calculating in a Monte Carlo integration sense, the integral of light passing through this aperture that all converges through x prime. Okay, so that's it. And if you do that, then you'll end up with a picture like this that's focused just on one plane in the dragon and has the correct circle of confusion and depth of field for everywhere else in this scene. I got a question here. Why do we assume there's two bunnies in this scene? It's just sort of a cartoon. You can have any scene that you want. And I just drew this to emphasize that we have to choose, where we will focus now. That's not something that we had to do before when we considered ray tracing through a pinhole camera model, because everything in the world is in focus. When we consider lens effects, you have to explicitly choose where in the world is going to be in focus. Otherwise, like with a real camera that has a bad autofocus algorithm, you'll just get some random picture focused at a random spot, and more likely it'll be focused at some depth that doesn't have anything there, and you'll just get a completely blurry picture. Okay, so the setup that I described is critical here as well. Okay. I want to talk about bokeh. Bokeh is the quality of the defocus areas. Bokeh is a really prized quality in people that care about photography, that spend time crafting and composing their pictures. Bokeh is the shape and quality of the out of focus blur. Okay, for small out of focus lights in the background of some photo, in this case, I guess there's some kind of color Christmas lights. The the bokeh is going to take on the shape of the lens aperture directly. Okay, so you can create kind of creative pictures that looks like this. This relates to a question that was asked earlier. Could you have a heart-shaped bokeh? You sure can. Okay, so here's an example of a picture taken with a camera with point lights in the background, different colors, and then that are creating these heart-shaped out of focus regions. How do you do that? It turns out you can do that with this kind of a lens. This is a 50 millimeter f1.8 Canon lens, very similar optical lenses available from most camera manufacturers, and a piece of dark paper has been put in front, serving as an iris where a heart has been cut out. I'm running a little bit short on time, so I won't go through all the details why, but it turns out this won't work for every lens. In fact, many lenses, this won't work. You'll get a blurry heart. But for this particular lens, because of certain optical properties of it are related to the exit pupil and its position, or its entrance pupil and position, it does work. If you're interested in those details, come chat with me in office hours and we can talk about it in detail. One thing I want you to note is that for real lenses, the bokeh can vary across the image. Can you see how it's actually there's a person's head blocking the dead center, but if it wasn't, you might notice that it's really circular, okay, the circle of confusion in the middle. And as you get towards the corners, they get into these interesting, kind of beautiful, if you like it, I do, but it gets into these sort of weird sort of shapes. It's almost like two circles sort of passing and eclipsing each other. And that has to do with the optical recipe inside the lens that's causing these kind of effects. Believe it or not, these kinds of properties for certain lenses are highly prized. This comes from one of the most expensive lenses that's available on the market, the Leica Noctilux 50mm f0.95. This is a highly prized optical device, and has a price tag to go with it. Okay. Now, how do those kind of effects occur? Well, it's come back to the topic that I raised at the beginning, is that modern lens designs are highly complex. They're not at all close to the thin lens model that we use today, okay? That assumes like a perfectly flat at a plane lens that takes all rays of light that are parallel and converges to a perfect point on the other side. No, real lens designs are thick, okay? They are significantly heavy. They have, look in here, there's like, over 12 pieces of glass inside this cross-section of this lens. Even in very, here's another example of like a cross-section through a real smartphone lens. This one had 4 pieces of glass. This was 10, 15 years ago. They've gotten more advanced with more lens elements these days. I showed you this example before. It keeps going. For things like microscope objectives, this has, a couple dozen pieces of glass inside it. And what's going on? It all has to do with like nothing, very mysterious is going on. Nothing's, like swept under the rug. It's just Snell's law, the refraction of rays of light through these glass elements, which are precision engineered and manufactured to very specific radiuses of curvature and with extremely accurate distances, thicknesses to each of these lens elements and alignment to each of these. They're all designed, computer-aided design, in order to provide the optical image quality and characteristics that one needs for a microscope or for a zoom lens that I showed earlier or for a smartphone lens. The problem that occurs is that you have geometric non-convergence of rays. I showed you if you have a simple analytic spherical lens here, which is, by the way, the easiest to manufacture at high quality in glass for various manufacturing related reasons, it just won't converge to a point. So real lenses versus ideal lenses. Real optical systems have many lens elements, and optical aberrations prevent the rays from converging perfectly. And what we've looked at in this lecture is a theoretical abstraction, but a very important theoretical abstraction that let us deduce many of the most salient and important visual characteristics of lenses, okay? So this end part of this lecture really is starting to touch on, well, how do real lenses work? And can we use them in computer graphics? It turns out, yeah. Okay, so here's a formula for a real lens. You could get this from a patent for a lens, for example, or from like optical engineering book. This is just a little table that describes exactly this lens here. It just describes the radius of curvature of each piece of glass. It tells you N sub D is the index or refraction of that piece of glass. V sub NO, V number is the dispersion quality. It just says how much light is going to change, how the index or refraction changes as a function of the wavelength of light, which will cause light to spill out into a rainbow, or spread into a rainbow, aperture size, thickness, and all that. So this just is a perfect CAD description of this lens. Maybe you can see where this is going. If you have this description, you can totally just put it into your ray tracer and apply Snell's law, and you can render photographs that look as if they were taken with real lenses, okay, according to these optical recipes. And this is a thing in computer graphics that's been done. Sometimes it's useful, for example, for integrating computer graphics imagery into cinematic footage that's been captured with real cameras. Here's an example of a telephoto, a normal 50mm, and a fisheye lens as an example. Okay, you can see some of the characteristics here. Telephoto and its shallow depth, its compression of depth of field. Here's the fisheye lens. that I showed you examples last lecture of the compositional characteristics of it. All these things can kind of come through, and all you do is you just ray trace these rays of light through. I just have two last slides. There's a bit of detail over it. In the interest of time, I'm going to breeze over it pretty quickly because my high level point on it is pretty simple. And I don't want to get belabored by the mathematics, which is not critical to the main point that I want to teach you, which is that it's really just Monte Carlo integration again in your ray tracer. And so one way to think about it is you model the world now as if there's a lens inside it. Okay, you model the whole 3D world and all the material characteristics. You put this engineering model of the lens recipe that I showed you before into your scene, and then you describe where the sensor position is. You have to figure out carefully what distance to put this at in order to focus at the right thing in the world again, just as you would if it was a real lens and a real camera. After that, you're just rendering what is the value of the irradiance on this sensor surface that would have resulted from that real 3D world above this camera and with this specific lens. So all you do is at every sensor pixel, you compute the integral of the rays incident on that pixel area arriving from all paths through the lens. And a way to do that is to choose, very similar to what I showed you before, you choose random positions x double prime on the back of this lens here, what we may call the exit pupil, and you just cast rays from x prime through x double prime. Now here's the difference. Before, with the thin lens equation, we could say, oh, x double prime and this x prime here, from the thin lens equation, I can tell you exactly the x triple prime point in the world that it's going to have to go through. You can't do that here, okay? You're going to have to ray trace it just by hitting this first piece of glass, bending the ray of light with Snell's law, going to the next lens element, and so on and so forth, and out into the world. But no problem. That's just recursive ray tracing, exactly as you've looked at it in class. So that's all you do. Turns out to get exactly the right irradiance, there's some radiometry involved, okay? But this is like from radiometry lecture. It's accounting for all of the correct factors of cosine law, projected solid angle, R-squared terms for fall off of light, if those are appropriate. And it turns out there's a, would you believe it? People have done this for real cameras and sensors, and there's a very famous cosine to the fourth theta term here, where theta is the angle between the this ray of light between the sensor and the lens and this optical axis, okay, that theta. And that's it. So there's some radiometry, incorporate Monte Carlo, apply the Snell's law that you're going to get to play around with in your assignments. And after that's Monte Carlo integration. Okay, so that's how you could use real lens designs and trace it through physically accurate in ray tracers as well. All right, that's it. And a things to remember slide, as I usually do. Hey, thanks a lot, folks. That's it for today. Let me see. Is Xiaosong still here? A question I didn't get to. That's okay. We'll pick it up in some other venue. All right, folks. Have a good afternoon. See you later. Have a good weekend. Oh, I got a question. Is Iman still here? Yeah, Iman's still here. Iman asks, can you explain bokeh again? Yeah, sure. Bokeh is let me stop sharing my screen. Let me just do that again. Okay, so bokeh is the shape and the quality of this out of focus blur. And I was just showing some examples where it's not always a circle. Okay, and for real lenses, it's actually never a circle. So you could, make it something else yourself if you wanted. I noted how it can change over the, depending on which part of the image we're looking at. And the reason this comes up is because I didn't get a chance to describe this in the main lecture, but if you sort of think of the lens as like an optical element that, is long, has many pieces of glass, it's kind of like a tube of glass, if you will. And if you think of looking down a tube, this is not an exact analogy, but it'll give you some intuition about it. If you imagine sort of taking like a cardboard tube and looking down it, then if you move it away from your eye a little bit and move from one side to the other, you'll find that you can't look down the whole length of the tube. If you're right in the middle, you can look down the whole length. But if you move to the side a little bit, the front opening versus the back opening will start to sort of eclipse versus one another. They'll slip against one another and start to block each other partially. That's similar to the kind of effect that's happening here, although it's a little bit more nonlinear because of the kind of optics that are in between. Okay, there's all those lens elements and their curvature, their optical curvature. But that's what bokeh is the quality and shape of these. Actually, bokeh, I didn't show that example here, but bokeh is often looked at when you have a lens that I don't have a picture here, but the iris inside the lens is created with sort of a mechanical metal structure that as it twists, they sort of will close down in a spiral shape, typically to close down the aperture. Okay. Now, how many pieces of metal are involved in that spiral closing down will sort of define like how many sides of a polygon you see as it closes down. So sometimes you'll see in the bokeh for when you've stopped the lens down to a particular size, you'll actually see instead of it being round even in the center, it'll kind of look like a polygon. You might even be able to count the number of sides, 5 polygons, 7, 9. You could count the number of blades, metal blades in the iris is the way it's sometimes described. And people that care a lot about photography might argue a lot about the shape of that bokeh and whether they like that quality. Okay. It's subjective at the end of the day, but smooth and sharp is smooth, and sometimes people talk about it as creamy is the quality of the bokeh that people often look for in sort of a prized or high quality photography lens. To answer the question? Oh, I lost my chat. Good. All right. Any other questions for today? All right, folks. Hey, good to see you all. I will catch up with you later.